Have you ever looked at a really complex system? I don't know, like a company's org chart or maybe a tangled web of fiber optic cables and just felt completely overwhelmed.
Oh, absolutely. It's that feeling of paralysis, right? We're looking at this chaotic mess and you just wish you had a key, some kind of blueprint to its underlying structure.
And that's exactly what we're tackling today. We want to move from just seeing the tangle to actually scientifically unraveling it.
We're going to show you how to do that. The mission for this deep dive is to shortcut you past the usual brute force methods and get you straight to, well, intelligent design.
That's it. We are exploring a core concept in high performance algorithm theory, something from graph theory called ear decomposition. The whole principle is simple, but it's so profound. Structure dictates strategy.
You stop guessing, you start designing. We're showing you how a deep structural understanding of your data can unlock just massive efficiency gains.
In problems that seemed, way too complex before.
Exactly. We're helping you stop exploring blindly and start focusing with surgical precision.
Okay, so let's ground this in the real world. Networks or graphs, they're everywhere. They model supply chains, social connections, everything. They're simple in concept,
Yeah.
but why is it so brutally expensive to calculate their global properties when they scale up?
Well, the problem isn't just the sheer number of nodes, it's the lack of structural awareness in the tools we normally use.
You mean the standard algorithms?
Right. The workhorses like breadth first search BFS and depth first search DFS, they are at their core fundamentally blind. They explain every single node and every path with pretty much equal weight.
So they're treating a critical network hub the exact same way they treat some dead-end branch.
Precisely. They waste an incredible amount of computation on the structurally irrelevant parts of the graph. Things like bridges or entire tree-like appendages.
These dead ends?
We call them dead ends because they don't offer any alternative paths. They simply don't contribute to things like redundancy or cycles.
And cycles are, they're the holy grail for network analysis,
Right.
right? They represent robustness, different routes, complexity.
They do. So if an algorithm is out there searching for a cycle, but it's spending most of its time in these tree-like
That
bits,
just sounds like a massive architectural flaw.
it absolutely is. I mean, think about the fundamental knowledge we already have. We know for a fact that an undirected cycle has to be completely contained within what's called a biconnected component, or a BCC.
And that component has to be at least size 3, right?
At least 3 nodes. So if you're using a standard traversal that just ignores that basic structure, you are searching a huge, totally irrelevant space where cycles are structurally impossible.
So the challenge isn't really to search faster. It's to understand the graph's architecture before you even start the search.
Yeah.
You have to isolate the complex core first.
And that is exactly what ear decomposition, or ED, gives us. It's a systematic, iterative way to take that tangled network and just unravel it layer by layer.
Let's use the analogy from the source materials. Like you're unraveling a complex chain link fence. You're not trying to analyze the whole mesh at once.
No, of course not. You start with the very first loop. We call that P dollars. That's your initial simplest structure.
Okay.
Then you sequentially attach these secondary paths, and those are known as ears, PD dollars, P22, and so on. An ear is really just a new path, but its endpoints have to attach to the structure you've already built.
But the middle part of the path is all new.
All the interior edges and nodes, they're completely fresh material.
So this turns a huge, complex, simultaneous problem into a systematic, sequential one. Instead of one giant hairball, you have a series of defined, manageable steps.
And that leads to 3 distinct advantages. The superpowers, if you will, of using ED in algorithm design. It's fascinating how structural knowledge translates directly into computational leverage.
Okay, so what's the first big payoff for an algorithm designer?
The first one is foundational. ED characterizes connectivity. It takes these abstract network properties, like resilience, and turns them into definitive, testable structural conditions. You don't just hope your network is robust,
You prove it.
you prove it through its decomposition.
That structural proof is so critical. All right, the second superpower. This one speaks right to the need for speed. How does ED enable parallelism?
This is a huge shift. Many of our foundational graph algorithms, especially the ones that rely on depth-first search, are inherently serial. You have to finish step n before you can even think about starting step n plus 1.
Right, it's a bottleneck.
ED breaks that dependency. Because each new ear, each Paiba law, is only defined by its 2 attachment points to the previous structure, you can often process these ears independently and simultaneously.
Wait a second, so instead of one long DFS sweep, We can hand off the analysis of P$11 to one processor, 2 pi to 2 to another, and P2.3 to a third, all at the same time.
That's it. You turn a slow serial task into a highly accelerated parallel process. The structure of the decomposition itself dictates your strategy for distributing the computation.
And the third superpower, this seems to tie it all together. ED simplifies complexity.
It does. Once the graph is decomposed, we can systematically remove all those simple degree 2 nodes we talked about, the non-essential links that just stretch things out. We isolate the complex core, which is where the real computation needs to happen.
So the algorithm can ignore all the structural padding and just focus on the actual hard problem.
That's the idea.
Okay, let's go back and focus on that first superpower, characterizing connectivity. This is where the theory provides real, concrete guarantees for building survivable networks.
Right, we can formally test for robustness. Takes UH connectivity being bridgeless, which is really the baseline for survivability. A graph is two-edge connected if and only if it has an ear decomposition.
And that's critical for things like what, fiber optic networks?
Absolutely. WDM fiber optic networks. It guarantees that traffic can withstand any single physical link failure.
That's a powerful guarantee for a broken link. But what about when a whole node goes down? That's two vertex connectivity or biconnectivity. Why does that need a slightly stricter type of decomposition?
Well, that's the nuance of the structural theory. Node failure is much more severe than edge failure, so the structure has to be more robust. A graph is biconnected if and only if it has an open ear decomposition.
And the key difference there is what?
It's subtle but vital. In an open ED, every ear after the very first one has to connect two distinct vertices.
Okay, so if an ear just looped back to a single vertex, then removing that one vertex would disconnect the whole loop from the rest of the structure. Is that right?
That's it, exactly. That single point is called an articulation point, and taking it out breaks the network. The OpenEDD guarantees that your redundancy runs through two different parts of the existing structure. It formally defines those robust subnetworks, the BCCs.
And this extends even higher, right? To three vertex connectivity, which needs a non-separating ear decomposition. We're moving from just describing robustness to having an actual blueprint.
A blueprint for how to construct or analyze these highly robust networks. And let's just revisit the parallelism payoff with a concrete example. Think about planarity and SNA numbering.
Okay, planarity testing. That's a core step in, like graph drawing and designing VLSI chips.
Right. And traditional S numbering, which you need for that, relies on DFS. And as we said, DFS is serial. If you're laying out a massive integrated circuit, that bottleneck is just unacceptable.
So what's the alternative?
The alternative is an ear decomposition search, or EDS. We use that structural breakdown to perform computations in parallel. This reorganization lets us compute snumbering in logarithmic time on parallel machines.
Which massively speeds up chip design.
Chip design, complex system visualization, you name it. It's the difference between doing things one by one sequentially and getting near instantaneous parallel results.
Okay, let's take all this incredible theory and smash it up against a really hard problem.
Yeah.
One of the classic NP hard problems, finding minimal covers.
Yes. This is where you see the theory turn into a massive practical breakthrough. A lot of powerful approximation algorithms for NP hard problems use something called the primal dual framework.
In this framework, it works by iteratively searching for violating structures, right?
Correct. And those violating structures, the things that tell you your current solution isn't quite right, they're almost always cycles.
I see where this is going.
The search for a violating cycle is the most demanding part of the standard PD cover algorithm. It's typically a blind, brute force search across the entire graph.
So for a big network, the algorithm is spending almost all its time searching for violations in places where they couldn't possibly exist.
That is the number one performance bottleneck.
So we've got a conceptually powerful algorithm, but its implementation is hobbled by this structurally unintelligent search. We need to go from a sledgehammer to a scalpel.
And the breakthrough is to embed the structural analysis directly into the algorithm, make the search hyper-focused. We call it intelligence up front. We apply a two-stage structural filter before the main search even begins.
Okay, so stage one.
Stage one is the big filter, the BCC filter. We start by identifying all the biconnected components.
Because we know any cycle must be inside a BCC of size 3 or more.
You've got it. This simple upfront analysis lets us immediately throw out all the bridges, all the leaves, all those simple tree-like parts of the graph. We've just surgically isolated the parts of the graph that can even contain a cycle.
That makes perfect sense. We've just carved away all the dead wood. But even inside a BCC, there must be edges that don't contribute to complex cycles.
Yeah.
How do you filter what's left?
That's stage two, the ear filter. Inside each of those isolated BCCs, we perform an ear decomposition. Then we discard any edges that don't belong to an ear of length 3 or more.
Why length 3?
Because if an ear is just length 1 or 2, it's just too simple. It can't form the kind of complex, violating cycle we're looking for in this context.
So we're creating a refined, cyclable skeleton of the
Yeah.
graph.
Yeah.
We only keep the structures where a violation is actually mathematically possible.
That's it. And the efficiency gain it's just staggering. For typical sparse, scale-free networks, the kind of graphs that model the internet or airline routes.
Real-world systems.
Yes, real-world systems. This two-stage pre-filtering can ignore up to 80% of all edges before the core search algorithm even fires up.
80%.
Yeah.
That's not optimization. That's a total redefinition of the problem space.
Mhm.
You're taking an NP hard problem, and before you even start the heavy lifting, you've cut its size by 4/5.
This is what we mean by structure dictates strategy.
Wow. Okay, so that reduced search space completely solves the speed problem. But what about the quality? You mentioned that these primal dual algorithms can be greedy. Why is that greediness a danger for finding a truly minimal cover?
The primal dual framework, it often focuses on local optimization. That means it adds nodes to the cover based on whatever looks best right now.
I see. And that can lead to a bloated solution.
It frequently results in a solution that works, sure, but it includes redundant nodes. Nodes that aren't actually necessary to cover the whole network. The cover is non-minimal. It's fat, not lean.
So we need one more surgical step at the end to guarantee minimality. How does the new workflow make sure the final cover is as lean as possible?
We use a really elegant post-processing phase called the reverse delete strategy. Once the initial and possibly non-minimal cover is found, we just store the order in which all the nodes were added. Let's say V dollar through a V dollar.
Well, then you just work backwards.
You work backwards. You start at the last node added, V dollars. You temporarily remove it from the cover, and you check if that removal causes any of the original violations to reappear.
And if no violations pop up?
If nothing reappears, $7 was redundant and you can permanently discard it. If a violation does come back, well, you put it back in the cover and move on to check every other out.
That's a perfect mechanism. By going backward, you're testing how necessary each node was in the context of the nodes that were selected before it.
And the result is a totally transformed workflow. You go from a massive brute force search that gives you a potentially redundant result
to a dramatically filtered search space with guaranteed minimality at the end.
So what this whole deep dive shows, I think, is the immense leverage that structure provides. Structural theory, like ear decomposition, it's not some detour into academic abstraction. It is the most direct, the most intelligent path to building superior algorithms.
It's proof that investing time upfront to understand the connectivity of a network lets you compute these fundamental, hard-to-find global properties with a speed and precision that just wasn't possible before.
Right.
I think the biggest takeaway here for you listening is that every tangled problem has an underlying structure that's just waiting to be revealed.
Yeah.
If you can find that initial loop, that $10 and then the ears that attach to it, you can transform chaos into a solvable sequence.
And that's a lesson that extends so far beyond computer science. If a focused structural analysis can give us an 80% efficiency gain in abstract graphs, you have to ask, where else? Where else in complex real-world systems, economic modeling, supply chains, even biological networks, might finding the correct structural thread to pull give you a similar advantage?
The ultimate challenge is always figuring out which thread to pull from the tangled mess you're facing.
Find the structure, and the strategy will follow.
Until next time, keep diving deep.